Hello, everyone. Thanks for joining. Today we have a talk by Mirko Bracale. Mirko is a PhD student at ISTerre, and he's also a part of the SPIN network. And his research revolves around wave field gradient methods and what kind of new information we can get from them. So without further ado, I give the word to Mirko.
Okay, thank you, Julius. So today I'm going to show you a study that will be presented also at AGU in a couple of weeks. Just the version that will be presented at AGU will be a little bit shorter because at AGU we have only 7 minutes. So here I added some more details about this study. So feel free to interrupt if something is not clear, and of course after we'll have some questions. So this study involves numerical simulation in eye scattering mediums, and the aim of this study was to be able to correctly to show that we are able to correctly reproduce the propagation of seismic waves in highly scattering mediums. And why this is important? So we can use some scattering parameters. Through those scattering parameters, we can build an heterogeneous medium, and then using forward modeling, we can propagate waves inside this medium. Well, if we are able to correctly represent the behavior of waves in a scattering mediums, this means also that if we use field data, we could be able to perform inverse modeling and then to retrieve the scattering parameters of the medium. And as I will show in this presentation, rotational sensors and distributed acoustic sensing play a crucial role in distinguishing between shear and longitudinal motion. So have a really important role into this process. And of course, this could be interesting also for people who are performing FWI. And in this case, for example, we can see that it could be possible to use also coda waves. Of course, once that we are sure that our medium, our simulations are correctly representing scattered waves, we can also investigate the behavior of the different fields, so of rotation, strain, and velocity fields in different conditions. In this case, for example, I'm just showing some examples from one of the simulations. So my contribution in this, let's say, in this code for forward modeling was the one that I'm showing here. So basically, this code was made by Romain Brossier in the consortium of SciScope, which includes also some companies. The old version of this code, which is a spectral element simulation code, was outputting only the displacement, so the 3 components of the displacement. With my new implementation, it has been possible to retrieve also 3 components of the strain, so the normal strain, and 3 components of the rotation. So in this case, I didn't have to make explicit computation at the end because I was already getting them as output. So I just put an introduction here just to be sure that we understand, let's say, the following slides. Scattered waves, coda waves, how they are generated. There is no unique definition of coda waves, but we can say that coda is the part of the signal which envelope is smoothly decreasing toward time. And these coda waves are generated by scattering. So basically, waves that are generated at the source are interacting with some heterogeneities in the subsurface, inside the medium, not only in the subsurface. And then they get to the receiver with a random phase and random amplitude. So already here we understand 2 important concepts. One is that we need to in order to generate coda waves, we need to introduce some heterogeneities in the medium. And second, that this is a stochastic process. And so the first thing that we want to understand is how to build a medium which is realistic, with the realistically represent an heterogeneous medium. So we will think, for example, to make just a medium in which we just put a randomly distributed value that fluctuates around an average value, and we could use that. But this is not physically representative of the real world, the real physics. And indeed, what is generally done, and what we did, is to filter this medium using a specific filter. In this case, we use the Laplacian filter, but there are also other filters that could be used. Okay, so we need to filter this medium, and in this case, we use Laplacian filter, and what we obtain is shown on the right. Of course, we added also an offset to have let's say an average representative of the velocity propagation of waves. In this case, for example, I'm showing the model related to P waves velocity. So this model, this is just a slice of the model, but the model is a 3D, is a fully 3D model. So this is what we obtain, and we investigate three aspects with increasing heterogeneities. So considering 10%, 17%, and 25% standard deviation of heterogeneity. As I said before, the coda are generated by a stochastic process. So basically, the properties that we can study in this kind of mediums are properties that comes from statistics, which means that we need to use many to average over a lot of realization in order to get something meaningful for the medium. Generally, what is done in this case is to use what is called an ensemble average. So every time is build a new medium around other many simulations. So we need to run a lot of simulations, but the problem is that in my case, one simulation lasts for about 6 hours. So it was not possible clearly to perform thousands of simulation. A way around, in this case, is to perform what is called a spatial average, which needs just one realization. Of course, this comes with some conditions and assumption. In this case, we need to use an isotropic source, and the receivers must be sufficiently spaced. And this is because we need, there is an assumption. So waves that reach different receivers needs to have interacted with different heterogeneities, which means that the paths needs to be independent. Okay, I'm showing here one of the simulation. Again, this is just a slide. We have an isotropic source in the center of the medium. We see this polarization just because this is the vertical component of the velocity. And the first thing that we looked at was the decay of the coherent field. So the coherent field is generated by P waves. What we did is we used the configuration that I'm showing on the left. So we could put an isotropic source in the center of the medium, and then we surround this source with many shells of receivers. We turn these receivers in order to retrieve the radial and transverse component, and then doing the average over a shell of the radial component of the displacement, we were able to retrieve what is generally defined as a coherent field. So this field is decaying not only because of geometrical spreading, but also because there is an interaction with the scatterer, and so part of the decay is due to the scattering process inside this medium. Indeed, we can see that, for example, at 2 kilometers at the shell, which is located at 2 kilometers far from the source, the shape of the signal is really well preserved. While if we go, for example, at 17 kilometers, we see that basically this average is not enough for us to retrieve the correct shape of the coherent field, because the effect of the heterogeneity is more and more as far as we will go from the so far from the source. So we can study through the decay of the coherent field the scattering mean free path, which is a key parameter in the scattering studies, which represent the average distance over which a seismic ray travels before interacting with any heterogeneities present in the medium. So we made linear. We use this relation that I'm showing here. So at all the frequencies of our signal, and we retrieve the scattering mean free path, which clearly depends from the frequency. In this case, we also made a comparison between the scattering mean free path compute with our simulation with the one compute using Monte Carlo methods and the radiative transfer equation with Born approximation. This code for the comparison was provided by Ludovic Majoran. So what we can see in this case is that not all the frequencies are well represented, and indeed a good agreement we can say is found between 0.7, 0.8 Hertz and 2.933 Hertz. So in this using this analysis, we can say that at least we can be sure from, let's say, that those frequencies are well represented. So in the analysis that I'm going to show in the next slides, we filter the signal exactly in this frequency range. So the first thing that we can see is we can look at is how the energy is how is the energy of the different observables through the time at different distance from the center. And so I'm showing, for example, the energy of the displacement, the strain, and the rotation per component, and of course, we can pick so the P waves, which is the first arrival, and we see that is really clear in the, for example, in the displacement and the strain, while in the rotation, of course, we don't have compression, so we don't see clearly the P wave. We see something because especially if we go farther at a greater distance from the center, because there is a mode conversion. So basically the P waves generate some conversion, and so we still see some S waves. And then we can pick also the S waves that are coming after, which are extremely visible in the rotation. So it's the peak of the energy of the rotation. This let's say a simulation that I'm showing here was the simulation which the fluctuation of the heterogeneities was 10%. But as I said at the beginning, we performed also other simulations in which I could not do exactly the same analysis that I did for the first simulation, because the problem is that we are not able always to compare our findings with the theory, because we are using some codes for comparison, which use the Born approximation. But if the scattered field is really strong, as it could be if we increase the amount of scattering, then this is not an approximation that could be used. And that's why I'm showing mainly the simulation related to 10% standard deviation. So I'm showing, by the way, here also the other simulations, the result for the other simulations. So this is the total energy of the displacement, the strain, and the rotation. I picked the P and S waves at 2 kilometers for 17%, but as we can see, if we increase a lot the heterogeneities, we are not able to see clearly the peaks of the ballistic arrival, because they get completely destroyed, let's say, by scattering. And this is what happened in the other simulations. So we know that after the arrival of ballistic waves and coda, if we look at late coda, we should arrive in the so-called diffusive regime, which is a regime in which there is multiple scattering, and the flow of the energy is basically is a flux, is a smooth flux. And indeed, in our simulation, we see that if we go enough, let's say, if we analyze the decay of the energy at large distance, let's say at large time lapse, we observe this kind of decay. And we can also see that if we increase the number, the amount of scattering, we get before to this regime. And indeed, is what we observe. You can see that, for example, at 25% standard deviation, we observe this kind of decay way before than, for example, the first simulation, and we obtained something in the middle for the 17%. Then, if we look, let's say, we know also that so the shear and longitudinal energy, shear and longitudinal energy is constantly converting, and we know that if we compute the ratio between shear and longitudinal energy, at some point it should get to a specific value which is related to the properties of the medium. This depends from the frequency we are looking at. And indeed, for example, in our simulation, given the scattering properties of the medium and the time of our simulation, we don't get to equipartition. But what we did is to model, so to make other simulation using Monte Carlo approximation. Again, this is another code provided by Ludovic Majoran. And in this case, for example, we can see that both simulation get to the same result. So also in this case, we observe that the trend of the equipartition ratio is exactly preserved. So we see at 2 kilometers that our simulation are matching completely with this Monte Carlo simulation. At 6 kilometers, they are not matching completely, but this is also due to the fact that we are making a spatial average, and there could be some heterogeneities which change the let's say a bit the scattering around the ballistic arrival. But we see that, for example, at the end of the simulation, so around 17.5 seconds, we have a nice agreement. In the other cases, so for the other simulation, as I said before, we are not able anymore to use the Born approximation, but we know the value that we should reach at the end. And we see that if we increase the amount of scattering, we get closer to that value. And actually, if we consider 25% standard deviation, we reach perfectly equipartition. This is also shown basically in the plot that I'm showing up left. I also showing what is expected theoretically, which is the equipartition, how should evolve this ratio through time. And we can see that if we look at 25%, we should be almost at equipartition, while, for example, we are really far if we consider the 10% case. And indeed, we didn't reach yet the equipartition. So the simulation that I showed before was a simulation in a full medium with the full absorbing boundaries, source in the center. But of course, in the real data, we are in the real world, we will have a free surface, and indeed we performed other simulations considering free surface. So we put in this case a source at the surface to generate also more surface waves. And this is just a movie of this simulation. And in this case, this is a preliminary work. We had to use a different geometry of source and receiver disposition. We can see again the decay of the coherent field. Also, if it's affected way more, we can see from the scattering. Also, because due to the geometry, we could not use so many receivers around the source. And but we looked also in this case, for example, at the energy of the different of the several observables. In this case, we have really a lot of energy also at S waves and generated also by surface waves that we can see, for example, in the rotation, the components of the rotation. And we looked also at equipartition, which again, in this case, the fluctuation was 10%. Well, we don't reach equipartition, but we see that we reach the diffusion regime on the left. So this, let's say, concludes this presentation. So what we can conclude is that our simulation are able to correctly represent the physics of wave propagation in high scattering mediums, and that it is possible through using DAS and rotational sensor to characterize and monitor scattering properties of the medium. This, for example, could be something that could be used in fields, for example, for landslides or volcanic area. And then, of course, if we work with the full waveform inversion, we can start to think about including coda waves in the inversions. And so that's it for the moment. Thank you.